A él es de 50 minutos, ya vamos un poco retrasados.
A 2010, profesor de tiempo completo en técnicas de construcción de la Universidad de Roma, en la Sapienza. Desde 1963 ha dedicado su actividad profesional al campo de la ingeniería estructural, ganando particular experiencia en el diseño de proyectos avanzados e innovadores. En 1969 fue parte del equipo ganador para la licitación enfocada al desarrollo de ideas para cruzar el estrecho de Messina, así como parte del grupo ganador de la licitación para el diseño y construcción de este mismo puente. De 1980. Así como en Italia. En febrero de 2012 fue designado presidente del Comité Técnico Nacional, Puentes en Caminos de la PIARC. Ha escrito más de 100 trabajos, incluyendo libros y artículos sobre acero y estructura sismo resistente, de los cuales destaca Ingeniería Sísmica, publicado en Nueva York. Ha dado innumerables conferencias en Italia y alrededor del mundo, y ha sido llamado para presidir en congresos internacionales de gran prestigio. Recibamos, por favor, al profesor Michele Mele.
Señoras y señores, buenos días. Ladies and gentlemen, good morning. I will be very pleased to be here in this wonderful city, and I would like to thank very much all the organizers of this seminar to be invited to give you this presentation. The time I have is not so much, so I should be able only to give you some flash information about the design of this bridge. The title of my presentation is A Sustainable Design for a Bridge over the Po River. The Po River is the largest one and longest one bridge in Italy. What I will say before I start with presentation is that I talk about sustainable design. Be careful. I don't talk about sustainable technologies, because sustainable technologies are only a part of sustainable design. I mean that if we use only sustainable technology in a design, we can afford what environment needs. And to avoid this confusion that now there is in engineering, I think that PARC is going a very good work in these cycles in the bridge committee. Thank you. Okay. Okay. Let's start, I hope. Okay. Okay. On April 30, 2009, a span of an old reticular steel bridge connecting two very important parts of northern Italy, I mean the regions of Lombardy and Emily, suddenly collapsed after abundant rains that had swollen the river to 20 meters foot above its usual level, causing masonry piers and strongly increasing the stress state of some joints already stressed for fatigue. Luckily, nobody died, but as a consequence, a large of a very economical active part of our country was cut in two parts. But, as often happens with stories that start with an unfortunate event, what followed turned out to be one of the most innovative bridge projects now regarded as a leading example, and not only in Italy. In fact, what our road administration named ANAS decided to do does go, I don't know. What our administration decided to do, it was not repair the old bridge because it was not good for fatigue problems. It was very old. They need a larger platform. They need a more performance for hydraulic problems. And so Before. Okay. So, yes, I say next one. It's better. Okay? Yes, but to go on is this one. Only this one. Okay. Okay. So, they decided to build a new bridge, giving the job of this design to my office. The input was very clear. First of all, innovation. Innovation in architecture, innovation in structural concept, innovation in environmental aspects. And after saving the historical piers, we can not to do anything with the historical masonry piers, a largest platform and hydraulic section, high durability, and very important, time efficiency for design and construction in order not to have cut these two very important parts of our country. And the output of this input was this bridge that you see in these slides. About the characteristics of the bridge, 11 spans of about 75 meters for a total length of 800 meters for the bridge over the river, a platform more than 15 meters wide with one sidewalk, one cycle lane, and two traffic lanes, all in over an orthotropic steel plate. The deck is a continuous steel grid truss girder, 4.5 meters high, and on each masonry piers were put a steel capital 3.5 meters high, rigidly connected these steel capitals to the deck three-dimensional truss girder. And plus there was a viaduct approach of about 300 meters, but this viaduct approach is normal, is not subject of this presentation. You see the viaduct access and the span of the main bridge. About architecture, the shape of the bridge has sprung from the will to preserve the characteristics of lightness and transparency of the reticular structure of the old bridge. A reticular structure for that was proposed, but reinterpreted the reticulate structure in a modern way with a spatial three-dimensional conception of the lattice, and undoubtedly an original type. This is an original type for a bridge, with the almost total elimination of bolted joints and use of tubular profile with a circular section. About structure, okay. Some slides of this three-dimensional grid and capitals. Here are deformed by the slides. The structure was, as I said, a three-dimensional latticed structure where the traditional distinction among main beams, secondary beams, diaphragm completely disappears because each structural element plays a multifunctional role. You see some sketch of the three-dimensional structure. About hydraulics, the old deck had a height of 8 meters, and with the new bridge reducing the height of the deck truss girder to 4.5 meters, only 1/20 of the span height, and placing capitals of 3.5 meters on the piers, the hydraulic section was increased by more than 20% at the riverbed and about 80% in the floodplain area, where the greatest problem occurred in the event of floods. This certainly puts the structure in safe condition even in case of extraordinary floods. The site was seismic, not very strong seismic, but seismic. And about seismic resistance, I say only that the return period, the reference line was 75 years. The return period of the earthquake was 75 for the damaged limit states and 712 for ultimate limit states. What about seismic forces? The longitudinal one ones were greatly reduced thanks to the use of viscoelastic dissipative devices incorporated in the multidirectional bearings and transferred only to the bridge abutments. The transverse seismic ones managed in this way. For the damage limit states, they are given to the piers. The surplus of these transversal forces were cut thanks to the adoption of dissipative devices similar to those adopted for the longitudinal forces and arranged on the piers between the bearings, as you see in this slide. On the left you see the supports with the viscoelastic device incorporated in it. And on the right you see the seismic viscoelastic devices put on the bearings on each pier. About fatigue, every detail of the steel structure has been designed looking for a satisfactory compromise between aesthetical quality and resistance to cyclic loads. The number of warranted cycles has been increased to 5 million with the highest fatigue load, thus achieving practically an unlimited lifespan. Of particular delicacy was the design of the joints among the tubular profiles, obviously. These are all kinds of tubular joints. For the lower joints, subjected to the most critical fatigue conditions, 10 different solutions were compared to optimize statical performance and constructive simplicity, analyzing for each one the static resistance, the fatigue resistance, and the deformability in the elastic and elastoplastic fields. And at the end, choosing one of these solutions, the sixth one, has the best compromise. You see here the results for linear elastic analysis. These were the results for fatigues, and these for elastoplastic deformations. What about durability? Has been assured with a typological choice of the steel profiles and avoiding any possible stagnation of water in details. Adopting perfectly sealed deck joints, adopting welded joints for the primary connections, furthermore, with a hot galvanizing treatment for the tubular profile or closed section elements composed of welded steel plates, with a zinc metallization process for the lower currents at the corresponding joints. The lower joints, where are the more exposed to rains. Providing 2 special painting cycles for the platform plates, 3 for the other elements, and 2 more for the restoration works inside, with the result of raising the interval of extraordinary maintenance cycles to values estimable that we could estimate between 50 and 70 years. The masonry pillars, just a few words, were reinforced injecting resins and cement grouts, and only for 2 particularly damaged piers foundations were reinforced inserting micropiles with a diameter of 30 centimeters. Last but not least, environmental sustainability design, and it is for that I present this design in this seminar. The design solution was compared with 2 other possible alternatives, namely, 1, a steel box deck in ribbed plates, Second, a solution similar to the one chosen, but with the non-galvanized tubes and traditional painting cycles, comparing both the economic and environmental costs over the entire useful life of the structure. The economic evaluation conducted with life cycle cost analysis showed substantially comparable results. But the environmental one was not simply qualitative. This is very important. Not, as we say normally, environmental friendly. When we use only sustainable technologies, we made only an environmental friendly design. But we have made another thing. We have made an analytical evaluation. So our way of design was for sustainability was an environmental efficient analysis. I mean, conducted with LCA, life cycle assessment, evaluating the impacts on the life cycle, starting from the production of the material used up to the end life of the bridge, take also in account the residual values of the structures, as normally we say, from the cradle to the grave of the structure. The impacts considered were, for simplicity, were only the ones due to the global warming potential, GWP, that is the accumulation of greenhouse gases in the atmosphere, undoubtedly the most relevant in the construction sector, and in particular for the bridge, both quantitatively and for the induced effects in comparison with other impacts that we have disregarded, as photochemical ozone creation, potential acidification, and so on. So, the life cycle analysis was evaluated considering the global warming potential of any substance, of any materials, and technology produced in the process in terms of an equivalent GWP of carbon dioxide. At the end, resulted that the chosen solution had emission values of at least 10% less than the other items compared. But this result was achieved, be careful, neglecting two important factors. First, that the tubes used came from steel scrap. And second, the steel coming from the demolition of the old bridge was largely used, about 40%, for the production of high-quality non-welded tubular profiles and used in the construction of the new bridge. Some words about the construction. The project also included the constructive modalities of a large part of the structure, except for the orthotropic panels of the platform and the connecting nodes of the tubulars, creating inside a real steel workshop in the floodplain area on the right bank of the river sheds, on the river. The construction was made in 5 sheds, 3 fixed and 2 mobile, organized with an assembly line logic. In the first shed, the reticular web panel were assembled. In the second and third ones, 2 half-deck span were assembled together at a time. And then each one was carried on the elevated launching ramp with a system of rails, and here in the 4th shed was joined to the structure already built, and in the second one metallization and painting were carried out, proceeding finally to the launching on the roller conveyors positioned on the capitals placed over the piers. Times and costs. Steel white, 8,000 tons total, comprising the included access viaducts, cost 42 million euros, about 60 million of US dollars, times 7 months for preliminary and final design for having all approvals, demolition and construction of a temporary floating steel bridge, 11 months for the bridge construction. And in this way was possible with this realization to celebrate the first 150 years of the Italy unification, lightning in this bridge with these three colors of our country and of your country. 2 words to conclude about the awards that this design has obtained. In 2010, the Demolition Award in London. Then a National Geographic Channel decided to make a documentary named Mega Demolition about demolition. About the design has achieved the Bentley Certificate of Achievement in 2012 for innovation in bridges. And finally, but not last, the bridge has achieved the EPD certificate, I mean the Environmental Product Certificate, and that is the first big infrastructure in the world to have obtained this kind of certificate. Thanks.